Hi, my name is Behrad. I'm a software architect at Aerospike. The title of my talk is Achieving Cache Level Performance Without Storing Data in RAM. This concept seems a little bit bizarre, but the technology landscape is moving very rapidly. Many things that we have today were unthinkable a few years ago. I remember when I was 6 or 7 years old, there was this TV program that I was obsessed with. This TV program was aired at a specific time during the day. If I wasn't in front of the TV exactly at that time, I couldn't watch the program in any other way. I remember back in the day, I went to my brother and I said that it would have been great if we could watch the TV channels on an on-demand basis. I remember my brother told me that this is impossible because for that to happen, the antenna that is sending the signal for the TV sets has to send a different signal to every TV set in the country. And that's something that is impossible. And I was convinced that it is not doable. But everything that we are watching today, probably this video that you're watching right now, is watched on demand. So if you want to learn a little bit about how a database like Aerospike can achieve a cache level performance without relying too much on RAM, let's fire up the engines and go on a journey to find out about the changes in the technology landscape. For a database, you have to store the data in the computer. Computers usually have two components for storing the data. One of them is the disk, the other one is the memory. These two components, although they are storing data, they have very opposing characteristics. So what I mean is that memory, for example, is very fast. The response time to a memory module is usually in order of a microsecond. But when you go to the disk, the response times are a few tens of microseconds, right? So it is order of magnitude slower than memory. It's not only the response time that the disk is slow, it's also the throughput that memory is much better in. So a normal module of memory that you can get in the market, it can do around 50 to 60 gigabytes per second in terms of throughput. Normal disks are around a few gigabytes. The best disk that you can get in the market can go up to around 12 gigabytes per second. But memory is very expensive. A 128 gigabyte module is around £800 here in the UK market. But you can buy the fastest disk, the disk that can do 12 gigabytes per second, for around £600 for 4 terabytes. So disk is significantly cheaper than memory. Also, as you can see, it was 4 terabytes and this one was 128 gigabytes. So we have a significantly more amount of disk than the amount of memory. Another difference is that the disk is persistent. If you write something to it, unless something happened to the disk has a physical damage, the data is going to be persistent in it, but the data that you write into the memory is volatile, meaning that if you restart the machine, the data will be lost. So when you're designing a database, you have to pick and choose which one of these, which data structure you want to put on which one of these components. So let's have a look at what kind of data structures or what kind of data we usually store in each of these components. Let's first talk about the data store, where you store the actual data. Of course, a database has to be persistent, so we usually store the data in the disk, right? So we store the data that we want to keep in the database in the disk. Then every database that you're familiar with has some kind of a primary index. The primary index allows you to find specific pieces of data that you are querying for. This data structure that you have, you need to access it very rapidly. And because it's a data structure that is indexing, it might be changing very rapidly. So other than having a very fast access to it, you need a lot of throughput to it as well. So we usually keep the primary index in memory. It's the same for the secondary index. Secondary index is usually stored in the memory as well. But lastly, most of the databases that you're familiar with has a caching part. This caching part basically keeps parts of the data that is already on disk in memory to give you a better performance. But we need to talk about this performance in a little bit more detail. So if you look at a computer, it's usually made of a bunch of memory, and it has a lot of disk as well. Usually the memory is in order of a few gigabytes, the disk is in order of a few terabytes. When you run a database on it, you use part of the memory as cache, part of it for the indices, and the data is stored on the disks. So when requests are coming in, if the requested data is available on the RAM, you can very quickly respond back. But if the data is not on the RAM, it's not in the cache, you have to go to the disk, fetch the data from the disk, bring it back, possibly write it into memory for the future accesses, and then send it to the user. So of course, it takes significantly longer for the data if it is not available in the cache. The requests are slower if the data is not available in the cache. So many people think that when you have a cache, when you're increasing the amount of memory that your database has, it's going to make your database work faster. We need to talk about this concept a little bit. Let me explain why. First, assume that you have a database and you are logging all of the response time that you are getting from this database for a long period of time. And then you created a sorted list from the fastest to the slowest query that you run against this database, right? So if you do something like that, you would get a chart like this. So the shorter lines means that the responses that were faster, the longer lines means that the responses were slower. Any database, or perhaps any system, is going to follow similar pattern that you see here. Almost all of the queries are going to be very fast and very close to each other. They are not going to be far away from each other. But there is a small percentage of queries that are taking significantly longer to process. These are the queries that happen during network failures, during disk failures, during network glitches. Your service was doing a garbage collection or whatever. Whenever those things happen, the queries are going to become a little bit longer. But generally, the shape is going to be like this. So for a database that you don't have enough memory to cache a lot of data, it is going to be exactly like this. But now, if you increase the amount of memory available to the database, so the data can be cached, the thing that is going to happen will be like this. So a lot of your queries start to work significantly faster, but the portion of the queries are not going to be changed almost at all because the data is not going to be in the cache and you still have to go to the disk to fetch them. So the response time will start to become like this. Basically, your fastest queries become faster, but when you go to the slower part of your queries, it doesn't really change anything. And this causes several problems in application development. The most famous one is that, but it works on my machine. So what I do mean with that? When you're doing developments and you are testing your application against the database, it's either of these two cases. You're either running the database locally, I don't know, either on your machine or through a Docker container or whatever, or you have a tiny virtual server somewhere that runs the database and you are connecting to that. In either of these cases, the database has a bunch of RAM, right? You will give it only 2 gigabytes of RAM. It doesn't have too much RAM. But it's still, when you give 2 gigabytes of RAM to this database, there's 2 gigabytes of RAM available for this database to cache the data. Unless you put more than 2 gigabytes of data in this database, when you test the database, you are only testing the performance of the cache. You never test what would happen if the database has to go to the disk, right? So you test your application against this test environment, which doesn't have too much resources, but it has enough RAM to store your test data that is hardly going to be even a gigabyte. And you would say that, oh, it is great. But then you take it to pre-prod environment and you run it, and it doesn't work. But it can be even working in the pre-prod environment. Why? Because usually your pre-prod environment is significantly larger, right? You don't put 2 gigabytes of RAM in your pre-prod environment. Many people run the exact same hardware that they have in production in their pre-prod environment, but they don't put the same amount of data they have in production in pre-prod, right? So again, when they test their application, they test the application against the data that is residing in the memory. not the data that is in the cache. So again, they prove something that is working in pre-prod, they go to production, and in production it fails. It can be even worse than that. You can put it in pre-production and everything works fine, and you put it in prod and everything is working fine, but then one day a pandemic happens and people start buying toilet papers left and right, and then suddenly the workload in your application starts to behave very, very differently, and suddenly everything fails without no one knowing what's happening, right? These are some of the implications that using a cache in front of the database is going to cause. But there's something even more important. It is very, very unlikely that increasing the size of the cache in front of the disk improves the latency of your application. So now I'm talking about the application. I'm not talking about individual requests. The difference is this. For your use case usually has to make several database calls to fulfill the actual requirement. For example, imagine you are a retailer and you want to show a web page to the customer that is showing an item that they are interested in buying. You have to fetch the information related to the item they want to buy from the database. You have to fetch the other items that they might be interested in. They have to fetch the other items that are usually bought with this item. You have to fetch the other items that are in the basket of this customer, and lots of other database calls. So you are making several calls to the database. Possibly each of them are happening on an individual microservice to fetch this information, and you assemble them together in one page and show them to the customer. The time that it takes for this page to load equals the longest running task that you had to run. So now, if you increase the amount of cache, well, increase the amount of memory that is available to the database, the thing that is going to happen is something like this. Some of these queries will hit the cache, and you get an order of magnitude better performance, but some of them are not going to hit the cache. Even if one doesn't hit the cache, the performance of that page load is not changed at all, right? So increasing the amount of RAM in your database is not really going to yield that much benefit. So at this point, you might be asking why every database in the market has some kind of a caching element that is using a lot of memory. And the answer to that is actually quite simple. Caching mainly enhances throughput, not latency. So let me remind you this picture that we saw earlier. We said that if the data is available in the memory, we return it back from the memory. If it is not, we go to the disk. We focused at the beginning that, oh, this is a better speed. But the speed is not the reason that we add the cache in front of the disk. This bit, that we are sending fewer requests to the disk, that's why we want to have a cache in front of the disk. That's why all database technologies that we are familiar with have some kind of a caching technology that reduce the throughput on the disk. But things have changed, as we said at the beginning of this talk. The modern disks that we have today are around 60 times faster than the disks that we had 10 to 15 years ago. And you might think that, oh, but everything is getting faster. But no, nothing else is getting faster. The CPUs that we have today have the exact same speed that they had 20 years ago, around 3 gigahertz. Nothing is getting faster, right? We are getting CPUs with more cores, so that is correct, but the CPUs are still working with the same clock speed. It's also true about our memory. The frequency of our memories are increasing as well, but 10%, 20%, 50%. Our memories are still in the same order as 20 years ago, but our disks has become 60 times faster. The disks that we had in 2010 could handle around 200 megabytes per second. As I said earlier in this talk, the disks that we have today can handle 12 gigabytes per second. That's 60 times improvement. So the questions become, is it possible to do something better than that using the throughput that we have available in our disks? So up until here, I talked about a bunch of concepts and I didn't go through them in much detail because we don't have enough time. If you're interested in this part of the talk, I have several articles that I explain a little bit more about the concepts that we discussed. But because this is not the topic that I want to talk today, I'm going to leave it and go back to the concept that, okay, now that we have these disks that can handle significantly more throughput, can we do anything better? And that thing that we can do better is that, can we build a database that doesn't have a caching layer to enhance its throughput problems? And that's basically what Aerospike is. Aerospike is a database that doesn't cache data to improve throughput problems that accessing to the disk is going to cause. So let's revisit this thing that we saw at the beginning. So we said that we usually keep the data on the disk or indices in memory, and we have a cache in memory as well. Traditional databases, they usually use like half of the memory for storing the indices, and they use the other half for caching parts of the data in memory to enhance the throughput of the system. So if we now remove the cache, we basically can use all of the memory available to us just for the index. So if you do that, now you can create a database that looks like this. You have a very, very large data structure, which is your index in memory. I'm showing it as a tree here, but it doesn't necessarily need to be a tree or a single tree. It can be many trees. But it's basically one data structure that holds reference to every single record in the database in the memory. And then you keep all of the data on the disk without any data structure. So what happens when a request comes in, you need to go to the memory part, to this massive data structure, and find the piece of data that you want in this data structure. This is going to be very, very fast, right? Because the access to the disk, as we said, is in order of a microsecond or less than a microsecond. So traversing this tree or trees to find the data that you are looking for is going to take a few microseconds. Then when you get there, when you get to the leaf that contains the record that you are looking for, you know the exact position of the data on the disk. So you can very surgically go to the disk and read the record that contains the information that you want and return it back. Access to the disk, the modern disks that we discussed, provide you with an excellent parallelization. So you can send hundreds or thousands of requests simultaneously to the disk. It's not like in the past that the disks had heads and you had to rejig the head, the location of the head to be able to read the data. In the modern disk, we can read them simultaneously. And also, the latency of the disk is not as bad. Modern disk, we said that they are like an order of magnitude slower than the RAM, but there is still an order of magnitude faster than the disks that we used to have in the past. So in order of tens of microseconds, you should be able to read the data from the disk. So you had a few microseconds reading the data from the memory, a few tens of microseconds reading the data from the disk, right? Now you have to put this information on network for the person who requested the data. The latency of your network is going to be in order of hundreds of microseconds. So the eventual response that the user is going to get is going to be roughly less than a millisecond. So that's what Aerospike can do. If you stored all of this data in memory, you could have only saved a few tens of microseconds, which are not guaranteed because you don't have that much guarantee on your network. So basically what I say that we can achieve an in-memory-like performance without storing the data in RAM. I mean this. But it is important to see that what is the implication of having such a technology for the applications that you're building. So we said that if you have a database that doesn't have enough memory, it's going to behave something like this. If you increase the amount of memory that is available to the database, the response times are going to improve like this. The fast part is going to become faster, but the slow part is not necessarily going to change much. With Aerospike, the performance that you get is something like this. Everything, unless those bad things that might happen in any network happens, everything is going to faster with Aerospike. And this has lots of interesting implications for you as developers. Let's talk about a few of them. So firstly, this is the concept that we talked about. we have a database that is storing the data on disk, but its performance is similar to the databases that just store the data in memory, right? It also means that it doesn't need a significant amount of memory to achieve that performance, which is, again, amazing thing to have. Another thing is that the response time for accessing the data across all of the data set remains the same. When you have a cache in front of the database, if you read the data that was written, I don't know, written or read recently, you are going to get a good performance. If it's a piece of information that you never retrieved in the past few weeks, it's going to be very, very slow. It's not like that with something like Aerospike. Because in Aerospike, the path that you go through to read the data that was written an hour ago is exactly the same as the path that you go through to read the data that was written 10 years ago. So access to all of your data is going to be as fast as having the data in memory. Next thing is that the access pattern, read and write, doesn't really matter for Aerospike. In most of this talk, I only talked about read access. I said that, yeah, your read is going to be as fast as memory. It's almost the same as write, but I just didn't talk about it because I didn't want to make this talk very complicated. But the read and write access follow the same patterns, and you achieve a cache-like performance from a database that is storing the data in a persistent storage, which is the disk. And then this one is very controversial. Usually when people think about something that is faster, they think that, oh, it should use more resources. For example, if you have a car, faster cars have larger engines, have more turbochargers, have, I don't know, they use more resources. But in computers, it's exactly the opposite. The only way that an algorithm can run faster than the other algorithm is that it's using fewer resources. It's using fewer CPU cycles. It's using fewer disk accesses. Unless you can reduce the amount of resources you use, your application wouldn't become faster. So Aerospike is fast because it uses fewer resources. If you use fewer resources to achieve something, your entire platform is going to shrink, which is great because you can reduce the amount of money you are spending on your resources, and it's going to be significantly easier to manage. But reducing the amount of resources has another benefit as well. The resources use a lot of electricity. So if you can reduce the amount of resources you use, you can significantly increase the sustainability of your company. What's not to like. So with that, I'm at the end of my talk. Hopefully you liked it, and I'd be happy to answer any questions you have. Thank you very much for listening to me.